Okay, welcome to 1.3 acceleration. So we've looked at position and displacement, we've looked at velocity. The last piece here is acceleration. Acceleration is the rate of change of velocity. Now, one of the useful ways to look at acceleration is with a velocity time graph. And a velocity time graph is one where the x-axis is time, and the y-axis is velocity. Okay, and so we're going to be looking at those. Oops, my y looks a bit like an x, so there you go, y-axis. Okay, and the other thing that we can look at is a position time graph. And our position time graph, if we have acceleration, position time graph is curved if we are accelerating. So, we'll take a look at a few graphs down here. We've got position time graphs. We've got a curved position time graph, so that means we're accelerating. And I just want to describe it a bit. So we can say here that position and velocity are increasing. So we're getting further and further away from our starting point. We're also getting faster and faster as we go. Okay, and so we can say that this is speeding up. And we can say that we're moving east. And again, the direction comes from the graph here, where it tells us that we're moving east. Okay, our second graph here, well, looks kind of similar, but instead of getting larger and larger, we're getting more and more negative. So we can say that D and V are decreasing. Sort of the opposite of the last graph. Now, are we speeding up or slowing down? Well, the answer is we're still actually speeding up. And all that's different is our direction. Instead of moving east, we're now moving west. But if you take a look at that picture, you can see that we're starting pretty slow, and we're getting faster and faster and faster and faster, just in the west direction. So we are still speeding up. So in fact, these two are very similar. Okay, graph C. Now, we're starting fast, and it seems like we're slowing down as we go. We're moving east, but we're slowing down. So that's what I'm going to put here. We're moving east, but we're slowing down. The first two we were speeding up, now we're slowing down. In this one also we're going fast, and then we're getting slower and slower. So we're slowing down again. But in this time, we're moving west. So it's important that you understand the difference between negative values and speeding up and slowing down. Just because we're negative here doesn't mean anything about our speed. The negative tells us our direction. It just tells us that we're moving west. But the speeding up or slowing down here is based on the shape of this curve. Okay, great. On the next page, that last one we were talking about position time graphs. Now we're going to say determining acceleration from a velocity time graph. Well, our equation for average acceleration is A average is equal to delta V over delta T. And I can expand that delta V. I can say that's Vf minus Vi. So the final velocity minus the initial velocity over delta T. And at this point, I just want to say something. I've been writing things like A average, and sometimes I write V average as well. These sorts of things. From now forwards, I'm just going to simplify that and only write A instead of writing A average. And that's because in this course, A is always going to be the same as A average, because in this course we're only ever talking about constant acceleration. So because A is always constant. Now that's only true in this course. It's certainly possible to have acceleration that's not constant, but in this course we're only ever talking about constant acceleration. So from now on, instead of writing this average after each time I write this, I'm just going to simplify and only write A. Okay? Good. And same for you. From now on, when you're writing A, feel free to just write A and not A average. Okay, so we're going to look at this velocity time graph. And remember we've said that the average velocity is just equal to the final velocity minus the initial over the change in time. It's the same as saying it's the slope of this graph. So, what is the acceleration of the skateboard in the figure above? Consider the motion between 0 and 10 seconds. So I circled 11, but actually we want to look at this value here. The way we do this is we can say A is equal to Vf minus Vi over delta t. And now we can plug in some values. So our final velocity here is 30. Our initial was 0. The change in time is going to be 10 seconds. And that gives us 3.0 meters per second squared in the south direction. And I say south because our graph tells us south. And there we go, that's my answer. That's my average acceleration. Okay, we have another question. When a rifle is fired, the rifle bullet accelerates from rest to 120 meters per second east in 1.3 times 10 to the negative 2 seconds as it travels down the rifle's barrel. So in a really short amount of time, this bullet starts going very fast. What is the bullet's average acceleration? Well, again, we're going to say A is equal to Vf minus Vi over delta t. So here we have our final is 120, our initial was 0, the delta t is 1.3 times 10 to the negative 2 seconds, and that comes out to 9231 meters per second squared, and our direction here is east. Now there's one piece I need to fix here. We're only given two digits, so I guess you could call this 3, but anyway, we're only giving 2 digits here. Means our answer needs to be 2 digits. And I'll use scientific notation here. There's my final answer. When a hockey player hits a hockey puck with his stick, the velocity of the puck changes from 8 meters per second north to 10 meters per second south over a time of 0.05 seconds. What's the average acceleration of the puck? Again, A equals Vf minus Vi over delta t. So our final velocity is 8, and our direction is north, minus our initial velocity was, our final velocity is 10 south. Our initial velocity was 8 north, and we're dividing by 0.05 seconds. Okay, we need to put these in the same direction. So I can still keep this as 10 meters per second south, but now I'm going to swap the sign, so 8 south over 0.05. So this gives me 2 over 0.05. I'm sorry, not 2. It gives me 18 over 0.05, which gives me a value. Oops, I've lost my my marker. There we go. Gives us a value of 360 meters per second squared in the south direction. And that's good. We can say that that 360 has 2 digits, so that's our final answer. Good. And one more problem like this. Actually, I am going to, let's solve this problem. It says a racehorse takes 2.7 seconds to accelerate from a trot to a gallop. If the horse's initial velocity is 3.61 meters per second west, and it experiences an acceleration of 2.77 meters per second squared west, what is the racehorse's velocity when it gallops? So the different thing about this one is that now we're looking for velocity, not acceleration. We're given the acceleration. We use the same starting equation. A is equal to Vf minus Vi over delta t. But now I'm going to rearrange this to solve for Vf. So A delta t plus Vi. Good. And now I can say that Vf is equal to, and just fill in my values. So I have my acceleration. The acceleration is 2.77 meters per second squared west. Delta t, 2.70 seconds. Plus my initial velocity. This gives me 11.089 meters per second west, which I need to simplify to 3 digits. Good. Okay, so that's how we're using this statement of acceleration using our 2 velocity measures, the initial and the final velocity. Okay, now I want to talk a bit more about motion with uniform and non-uniform velocity. So non-uniform velocity is where the speed is changing, the velocity is changing. But in both situations, we can find some interesting information from the graph. If we take the area under the graph, looking at the graph below, if you take this area, what that gives us is the displacement. So displacement is equal to the area under our velocity graph. So displacement, the area under this graph, you can see it's a triangle. So the area of a triangle is 1/2 times base times height. And so that's what our equation above is going to look like. 1/2 times base times height. So 1/2 times base times height. So the height is Vf plus Vi. The base is delta t. Okay. And this area is equal to the displacement. All right. So you can see how that works in this picture below. We have a base of 10 seconds. We have a height of 30 meters per second. So now we're going to find the displacement. What is the displacement represented by the graph above? Well, displacement is equal to 1/2 Vf plus Vi times delta t, which is equal to, now we can just plug in some values. We've got 30. So final is 30, initial is 0. and we multiply that by the base, so 10 seconds. It's 10 seconds here. Good, and this gives us 150 meters south. So that tells us that in those 10 seconds, that person traveled 150 meters. And it's really as simple as that. We just take the area under the graph, it gives us the displacement. Okay, now the next thing that we have, it says what is the displacement represented by the graph below over the time interval from 0 to 10 seconds? And notice that now this is non-uniform velocity, because for the first half it's increasing, for the second half it's steady. And we can do this fairly easily by breaking it into two pieces if we want to get the area. So we can say that this is piece 1 and this is piece 2. So for piece 1 I can get the area of that triangle. Delta D is equal to VF plus VI delta T. And sorry, I should have put 1/2 in there. 1/2 VF plus VI delta T. And now I can put some values in there. So my final velocity is 10. My initial was 0. So I've got 10 plus 0. And that happens over 5 seconds. So that's 25 meters south. Piece 2 is a rectangle. So I don't need to divide by half. I can just get the area of that whole piece there. Now actually I can use the same formula. Delta D equals this. So notice that this equation works in any situation. So I can use the same formula, but since VF and VI are the same, I could have made my life easier as well. But we'll just see how this looks here. We've got 1/2. VF is 10. VI is 10. So you see that by taking this 1/2 of 10 plus 10, basically what we're trying to do is we're trying to take the average of those two values. Same with up here, we were taking the average of the two values. Okay, the average of 10 and 10 is just 10. So 1/2 10 plus 10 times our time, which again is 5 seconds. So this ends up giving us 50 meters south. And now if I want to get the total displacement, well, this just looks like the total displacement equals displacement 1 plus displacement 2. Oops, 25 plus 50. Let's clean up that 0 there. So this is 75 meters in the south direction. And there we go. So that was a way of solving this problem, even where there's this strange changing speed, or changing velocity. Okay. We've got one more page here. And this is just talking about the difference between instantaneous velocity and average velocity. So this is an important distinction, because so far we've been talking all about averages. We've been saying, well, the average velocity over this time is this much, which hasn't been too much of a problem because usually our velocities have been constant or increasing at some steady rate. But here we have some different things going on. So first we want to talk about what is uniform acceleration. This is motion where the velocity changes at a constant rate. And so the velocity time graph would be a straight line. Not necessarily a horizontal line, but it would be a straight line, so it has a slope. Okay. And so We're going to talk about two types of velocity here. We have average velocity. This is the average over some time interval. And we'll just say that over this whole time interval, the average was this much. But the other thing we're looking at is instantaneous velocity. And this is instead the velocity at a specific instant in time. And the way we find this is by measuring the slope of a tangent on a position time graph. Okay, and a tangent, this is just a line that touches a graph at one point. I'll show you below what I mean exactly by a tangent. Okay, and so this is just to be able to distinguish between average and instantaneous velocity. So for instantaneous velocity, we need to get the slope of the tangent. If we want to find out exactly how fast I'm going at this time at 2 seconds, exactly how fast I was moving at 2 seconds, the only way to do that is to take a tangent. So you see this straight line here is a tangent. It just touches the graph at that one point and sort of falls away from it evenly on both sides. So we take that tangent and then we want to find its slope. And that's the only way that we can find out exactly how fast something was moving at that time. So we take the slope of this by finding the rise over the run. Okay, and so we're just going to answer these questions and then it's the end of the lesson. This says, consider the point on the curve in the figure above at 2 seconds on the x-axis. So this point here. What is the instantaneous velocity at this time? Well, we're going to find the slope of this tangent. So here we've got the rise. This is going from 4 up to 12. So here this is 8. And the run goes from 2 up to 4. So the run is 2. So what we can say here is that v is the slope of the tangent. And that's to say that it is the rise over run. Our rise was 8.0 meters east. Our run is 2.0 seconds. So this gives us 4.0 meters per second east. There we go. One last question. What is the average velocity of the object in the figure above over the time interval from 0 to 2 seconds? So here we have now average, 0 to 2 seconds. The average is just going to be the slope of the line between those 2 points. So I can take the final velocity. So I can say that the average velocity is equal to the final position. Well, we'll say it's delta d over delta t. So we ended at 4. We started at 0, and that happens over 2.0 seconds. So then we can say that our average velocity here is 2.0 meters per second east. And you can see that these two numbers are pretty different, so that at 2 seconds we're moving faster than the average up to that point. Okay, I know that this last bit of content might have been a bit challenging to wrap your head around. We will look at it a bit more in class, and if you do have any questions, please ask me and I can help you out. Okay, that's the end of the lesson, and I'll see you in the next one.